Okay, so this is our second video on probability, and today we want to talk about conditional probability and independence. So these should be concepts you've met before now. We talk about them in Year 10 and Year 11, so hopefully reasonably familiar, but it's really important that you get this right. It will feed into all the rest of the probability, particularly your understanding of conditional probability, if that's not right. Okay, so I'm going to start by giving you the formula, but I want us to then gradually explore why this is the formula, because conditional probability is actually a really logical thing, and if you get too bogged down in just understanding it as formula, you lose track of what's happening. But however, when we are calculating a conditional probability, that is the probability of A given B is how we read that. So by that I mean we're calculating the probability that A will happen given that we know that B has happened. Okay, and that is found by doing the probability of A intersection B divided by the probability of B. Okay, so the probability that both of the things will happen divided by the probability that the second thing will happen. Okay, but I want to talk through that, so let's take a step back from that formula. So let's just think a bit logically. Let's consider rolling a fair die. Okay, so we roll a fair die. What's the probability of rolling a 3? Okay, so the probability of rolling a 3 is going to be 1 out of 6. Great, we all know that. Okay, so now I'm going to tell you that I've rolled the die and I rolled an odd number. And now I want to know what's the probability that I rolled a 3. So what I've done for you is I've essentially reduced the sample space. So now what I'm asking you to work out is what is the probability of a 3 given that you know that the number is odd. Okay, so we know that I rolled an odd number, therefore it's only out of 3 possible outcomes. And 3 is one of those 3 possible outcomes, so that's going to be 1 in 3. This time I'll tell you that I rolled a number that's less than 5, which means I rolled 1, 2, 3, or 4. Now what's the probability I rolled a 3? So again, by telling you this condition, I've reduced the sample space for you. So what you're being asked to calculate here is the probability of a 3 given that the number is less than 5. Okay, so there are 4 possible numbers that are less than 5, and 3 is one of those, so 1 out of 4. Lastly, I'll tell you that I rolled an even number. So now what's the probability that I rolled a 3? So the probability of 3, given that the number I rolled was even, okay, so there's 3 possible even numbers, but none of those are a 3. So the probability of that is 0. Okay, so conditional probabilities are most easily seen in tree diagrams. So let's draw a tree diagram to represent this situation, then we'll talk about where the conditional probabilities are. So 2 bags contain marbles. Bag A contains 3 blue and 2 red marbles. Bag B contains 3 blue and 5 red marbles. First, a bag is randomly selected, and then a marble is randomly selected from that bag. Okay, so in this case our first choice is the bags, bag A or bag B. And then, from there, we either get a blue or a red marble. Okay, let's fill in some problems. So first First a bag is randomly selected. So we've got 2 bags, it's a random selection, so equally likely to be selected, so therefore half and half. Okay, then we know if we selected bag A has 3 blue and 2 red marbles. So the probability of choosing a blue-red marble from bag A is going to be 3 out of 5, and a red marble from bag A is 2 out of 5. Bag B has 3 blue and 5 red marbles. So the probability of getting a blue marble out of bag B is 3 out of 8 and 5 out of 8 for a red. Okay, so the key thing is that these 4 probabilities at the second stage are all conditional probabilities. That probability is the probability of choosing a blue marble, given that it came from bag A. This probability is the probability of choosing a red marble, given that it came from bag A. This probability is the probability of choosing a blue marble, given that it came from bag B. And this is the probability of choosing a red marble, given that it came from bag B. Okay, so part A, the first part here is, and I want to be clear about the distinction between these 2 questions. The first question says, what is the probability that a blue marble was selected from bag B? Okay, what's the probability that having done this experiment, I end up with a blue marble that came from bag B? The second question is, what is the probability that a blue marble was selected given that it came from bag B? So this time I'm telling you it definitely came from bag B. What's the probability it was blue? So the difference here is that the first question is asking you to find the probability that your marble came from bag B and was blue. The second question is asking you, what is the probability that you got a blue marble given that you know it came from bag B? And they're not the same thing. The probability of choosing a marble that is blue from bag B is 1/2 times 3/8. It's this pathway. Okay, that's the first question. So probability of choosing a blue marble probability of choosing bag B and then choosing a blue marble is 1/2 times 3/8. Okay, so 3/16. The probability of choosing a blue marble given that it came from bag B, this time you know it came from bag B. You're not making this choice. The whole diagram's essentially now starting from this point here. Given that it came from bag B, what's the probability that it was blue? That is 3/8. Okay, so it's really important that you read questions carefully, that you understand when it's saying, it's not going to say this is a conditional probability in the question. Okay, you have to be able to interpret that from the information. Most commonly you're going to see the phrase given that somewhere, but it doesn't necessarily have to say that. Okay, so you need to be able to really clearly interpret the information. Okay, let's have a look at conditional probability in a Venn diagram. So let's use a Venn diagram to represent the following information. So we've got 200 students. They are the French, it's about them studying French and German. So we've got two circles, French and German. Sample space contains the full 200 students. 42 study only French, so that's this section out here. Just French, no German. 25 study only German, that's this bit out here. 8 study both French and German, and then the remaining obviously study neither. So in total here we've got 50, 75. So there's 200 students in total in the survey, and so that means there's 125 that don't study either. Find the probability that a randomly selected student studies French and German. Okay, so that's the intersection. Probability of French and German, 8 out of 200. 4 is a common factor there, so that's 2 out of 50, which is 1 out of 25, sorry. Given that a randomly selected student studies German, find the probability that the student also studies French. Okay, so this is probability that someone studies French given that they study German. Okay, so given that they study German, we know they are one of these people in here. So we're now only talking about 33 people. We know that they're one of 33 people. What is the probability that one of those 33 people studies French? It's 8 out of those 33 people. Okay. Find the probability that a randomly selected student studies German given that they also study French. So probability that they study German given that they study French. So given that they study French, that's your sample space shrinker. Okay. Given that we know they are one of these people that studies French. Okay, they're one of those 50 people that study French. 8 out of those 50 people also study German. Okay, so that's 4 out of 25 in simplest form. Okay, so conditional probability is all about restricting the sample space. If we think back to the formula, we know that probability of A given B is the intersection A and B over B. That's what we're seeing happening here in a really logical way without necessarily relying on formula. This is the intersection of A and F and G over the probability of G, or the number of things in G. Okay, so it's the number of outcomes in F and G over the number of outcomes in G. This second one is the number of outcomes in F and G over the number of outcomes in F. Okay, so the denominator is the number of things in G or the number of things in F. That's what we're seeing in this formula. Probability of B goes on the denominator. Can I just be clear too about, because I know I did just slightly alter my language there. You can also, this formula is still the same if it, rather than use probability of A intersection B over probability of B, if it's the number of things in the intersection of A and B over the number of things in B. That's still the same thing as well. Okay. Alright, let's have a think about conditional probability in the probability table or Carnot map. So let's represent the following information in a Carnot map. In a particular workplace, 45% of employees are women and 60% of the employees have a university qualification. 80% of the female employees have a university qualification. Okay, so let's see what we've got here. the employees are either, now you can set it up as male or not, male and not male, female and not female. You can set it up as male and female, but then you don't get the, male and female. Or you could write, call this not female, or you could call this not male. Okay, but I guess maybe that's even controversial these days. Perhaps, the opposite of female is not necessarily, well, yes, actually, perhaps it's more gender inclusive to say female or not female. So up to you how you set it up for now. I don't want to overly complicate or politicize the problem. Okay, so we've got males and females, and we've got, well, technically if we follow the information in the question, it does only tell us about females. So let's make it females and not females, okay? And then they either have a university qualification or they don't have a university qualification. Okay, in previous examples, we've seen in our CAS map, we've put number of people. So total, it was 42 people in total. We wrote 42. Here we're given probabilities, so we're going to put probabilities. I'm going to always write decimals rather than percentages in the tables or Venn diagrams or on tree diagrams. So when we say that 45% of the employees are women, I'm going to say that the total number of females, or total proportion of females, is 0.45. 60% of the employees have a university. So because we're dealing in percentages, the total probabilities should, or the total percentages and proportions should all add up to 1. 60% of the employees have a university qualification. So 60% have a uni qualification. 80% of the female employees have a university qualification. Now we need to be a bit careful about that. We're not putting 0.8 here. That's a problem because that doesn't add to that and that doesn't add to that. So what we actually know is, what we've actually been given there is a conditional probability. That information is a conditional probability. That is the probability of someone having a university qualification given that they are female. That's 0.8. So we want to think about how we can use that in the Venn diagram. So hopefully most of you can see that if 45% of the females have a university qualification, sorry, 80% of the females have a university qualification, that's 80% of 0.45. Okay, so if we work that out, I'm going to come back to a different way you can think about that from what we know about conditional probability in a second. So that's 0.36. So the other thing we can think about is we know that the probability of U given F, we know from our formula, it is the probability, of U and F over the probability of F. And in this case, we know that that is 0.8. And probability of F is 0.45. And so therefore that tells us that the probability of U and F, which is the number we need for the CAS map, is going to be 0.8 times 0.45 when we rearrange that. Okay, and that was 0.36. So that confirms, but as I said, like conditional probability, it really is quite intuitive. You don't always need to go to the formula. There are certainly times where you need to utilize the formula and you must know it, but try to think logically about what's happening as well. Okay, so we've got enough information here to now fill in the rest of the table. So we must have 55% who are not females, 40% who don't have a university qualification. So if 0.36 plus something has to add to 0.45, so that is 0.09 of the females don't have university qualifications. No, sorry, that's not true. 0.09 of the employees are females who don't have university qualifications. And then here we need 0.36 plus something to add up to 0.6, so that is 0.24, and 0.09, so that's going to be 0.31, and we should be able to check it adds up in the other direction, which it does, so everything's good. Okay, what percentage of the employees are males without university qualification? So of the employees, it's not a conditional probability, so the probability out of the whole sample space that we have a male who does not have a university qualification, so that is we're assuming male is not female here. Apologies for the slightly non-inclusive language. So probability that an employee is not female and doesn't have a university qualification. So that is, we can see from table 0.31, it asks us for a percentage, so 31%. If a male employee is randomly selected, what is the probability that he has a university qualification? So if we select a male, so that's the condition. Given that we've selected a male or a not female, what is the probability that he has a university qualification? Probability of a uni qualification given not female. Okay, so again, we can think about the Carnot map. So given that the person is not female, so given that they're one of this 55% here, so we're only really now interested in this row of the table. What is the probability that they have a university qualification? So that is going to be 0.24 out of 0.55. 0.24 out of 0.55. Again, this is the probability of uni and not female, and this is the probability of female. So it fits, sorry, of not female, so it fits the rule. So 0.24 over 0.55, you're going to need to be able to work quite comfortably with decimals and fractions in the probability unit. So we can't leave decimals in fractions. I'm going to multiply both top and the bottom by 100, so that's 24 over 55. And then if I can simplify that further, which I can't in this case, I will. Given that a randomly selected employee has a university qualification, actually, so just before I move on, the previous question is an example where it didn't use the word given that. It said if a male employee is randomly selected. That could be rephrased to say, given that a male employee was selected. Okay. Right, second one, so given that a randomly selected employee has a university qualification, what is the probability that the employee is male? So the probability of not female given that they have a university qualification. So the condition is that they have a uni qualification, so that they are one of these 60% or 0.6. Okay. Probability out of that they're not female is going to be 0.24 out of 0.6. Okay, so it's going to be 0.24, which is the intersection of those two things, not female and university, over 0.6, which is the probability of university. So it's fitting the formula that we're familiar with. So again, multiplying top and bottom by 100 here, it's 24 over 60. 4 is a common factor there, so that's 6 on 15. So 12 is a common factor there, my apologies, so 2 on 5. Or 0.4 if you prefer. Okay, so conditional probability is about reducing the sample space. A given B means that we know B has happened, so only out of the outcomes where B has happened, what is the probability that A has also happened? So what we saw is if we want the probability of A given B, we're in the Venn diagram, we're just focusing on the B circle, and so it is the region in the overlap out of the total B circle, so that is the intersection of A and B over B. In the Venn diagram, it's the same. Given that B has happened, given that we're only talking about this information, what's the probability of A? So it is the intersection divided by B. And so we see that the formula fits very logically to our understanding of conditional probability. As I mentioned to you previously, you can divide two probabilities to find the probability of A intersection B, but you can also divide the number of ways it can happen. Okay, it's the same proportion. Alright, so let's now, if we need to use the formula, we can. A jar contains 25 marbles numbered 1 to 25. A marble is randomly drawn from the jar. What is the probability that a marble with a number greater than 10 is drawn, given that it has a number less than 20? Okay, so probability that we draw a number greater than 10, given that we draw a number that is less than 20. So if we think about our conditional probability, we're going to need the probability that we draw a number that is both greater than 10 and less than 20 over the probability that the number is less than 20. So you need to sort of be able to think about intersections of things. So if the number has to be both bigger than 10 and less than 20, that's because the number has to be between 10 and 20. That's the intersection over the probability that the number is less than 20. Okay, so there are 25 marbles, so the probability that the number, now I'm going to be clear about something here. So if we work out the probability of drawing a number between 10 and 20, so not equal to 10 and not equal to 20, so it can only be 11, 12, 13, 14, 15, 16, 17, 18, 19, okay, so that is 9 outcomes. So the probability of n being between 10 and 20 is 9 out of 25 over the probability of n being less than 20 is 19 out of 25. So what I want to be clear about, and this is where actually often we don't divide two probabilities because the denominators are the same. So if you think about this is 9 on 25 divided by 19 on 25, which is 9 on 25 times 25 on 19, the 25s cancel out and it's just 9 on 19. So actually, I probably wouldn't do this. I'd probably, rather than do the probabilities, I would do the number of ways, the number of outcomes, okay? And so that is 9 possible outcomes out of 19 possible outcomes, okay? All right, so previously it was mentioned that conditional probabilities can be clearly seen in tree diagrams. So as you know, this would be, we've got first stage B can either happen or not happen, and at second stage A can either happen or not happen. So at the first stage, this would just be the probability of B, and this would be the probability of not B. And then this is the probability of A given B, and this is the probability of not A given B. And this is the probability of A given not B, and this is the probability of not A given not B, okay? And if we were to multiply those two probabilities together, when we're multiplying along a branch, we're calculating an intersection. We're calculating the probability of A and B happening, and we would do that by doing probability of B times probability of A given B, which is also where this formula comes from. So if we divide both sides by probability of B, we again find that the probability of A given B is the intersection over the probability of B. Okay, so just thinking about how that all ties together. All right, let's have a look at an example. So Toby plays tennis and gets 65% of his first serves in. He wins the point 80% of the time when his first serve goes in, but only 40% of the time when his first serve doesn't go in. Find the probability that Tony wins the point given that he gets his first serve in, that Tony gets his first serve in given that he wins the point. Okay, so let's construct a tree diagram. So I go to a tree diagram when there's important sequence. You can't represent that in any other way. So in this situation, the first thing that happens is he either gets the serve in or not, and then based on that, he will either win the point or not. So that sequence is only able to be shown using the tree diagram. Okay, so he gets the serve in or not the serve in. Serve not in. Okay, that's the two options first. And then he either wins or loses the point. Okay, those are the things that happen. So Toby plays tennis, he gets 65% of his first serves in. So this is 0.65, which means that 35% don't go in. He wins the point 80% of the time when his first serve goes in. So that's a conditional probability. Probability of winning given the first serve went in. That's this probability here, 80%. And so the probability he'll lose if his first serve goes in is 20%. But he only wins the point 40% of the time when his first serve doesn't go in. So that's a conditional probability. Probability of winning given his first serve didn't go in is 40%, and so 60% that he'll lose that. Okay, so let's answer the questions here. So find the probability that Tony wins the point given that he gets his first serve in. So probability of win given serve in, oops, that's sitting in the tree diagram. That's that there. That's 0.8. We don't need any formulas. Okay. Find the probability that Tony gets his first serve in given that he wins. Okay, now this number's not in the tree diagram because we're sort of having to work backwards through the tree diagram here. Okay. The tree diagram is not set up as if he either wins or loses and then he either gets his first serve in or not. So this is where we're going to need to think through the formula. It helps us to be logical. So conditional probability is the intersection of the two things. So this is probability of getting serve in and winning over the second thing, which is the probability of winning. Okay, so probability he gets the serve in and wins is going to be 0.65 times 0.8. And then the probability that he wins, now there's two ways for him to win. He either gets the serve in and wins or doesn't get the serve in and wins. So there's two probabilities there. So probability of winning is 0.65 times 0.8. He gets the serve in and he wins, or he doesn't get the serve in and he wins. Okay, so the total way, there's two ways to win, so two different things to calculate there. All right, so let's work out what we've got here. So we've got 0.65 times 0.8 over 0.65 times 0.8 plus 0.35 times 0.4. Okay, so that's not a nice exact decimal. It does look like it's a recurring decimal, so I could write it as 0.78 recurring, but perhaps if I calculate those numerators and denominators separately, I can get an exact fraction. So that's 0.52 over 0.65 times 0.8 plus 0.35 times 0.4, which is 0.66, and so that is 52 on 66, multiplying top and bottom by 100. We can halve both of those to get 26 on 33. Which is nicer than rounding a decimal. Again, your work with fractions and decimals is going to be really tested throughout the probability. Example 3. Probability that Brian gets an A in his science test is 0.7, but if he has studied, this increases to 0.75. The probability of Brian studying for this test is 0.9. Find the probability that Brian does not get an A if he did not study. Okay, so again, I'm going to think tree diagram because the result depends on whether or not he studied. Okay, so he studies or doesn't study. Okay, and then he either gets an A or doesn't get an A. Okay, let's think about what we've got here because not all of this information goes straight in the tree diagram. The probability that Brian gets an A in his science test is 0.7. Okay, so there's two ways that he can get an A in his science test. He either studies and gets an A, or he doesn't study and still gets an A. And those together are 0.7. So the 0.7 doesn't go on the tree diagram anywhere. If he has studied, the probability that he gets an A is 0.75. So that's this. That's the probability of getting an A given that he studied. The probability of Brian studying is 0.9, which means the probability he won't study is 0.1. Find the probability that Brian does not get an A if he did not study. Okay, so find the probability he does not get an A if he did not study. So does not get an A if he did not study. This is the probability that we want to find ultimately. However, we're going to be able to calculate this probability using this 0.7. Okay, so we know that the probability that he gets an A is equal to the probability that he studies and gets an A, or the probability that he doesn't study but he still gets an A, and he gets an A. So that is, we know the probability of A is 0.7, we know the probability he studies and gets an A is 0.9 times 0.75, we know the probability that he doesn't study and gets an A is 0.1 times this unknown probability. Okay, but it's the only unknown, so we can solve for x. Okay, so we've got 0.7 is equal to 0.9 times 0.75 is 0.675 plus 0.1x. Okay, so let's subtracting 0.675 from 0.7 is 0.025. It's 0.1x, and so x is 0.025 over 0.1. Now again, if we were to multiply both by 1,000 here, so we get rid of the decimals, that's going to be 25 over, and multiplying by 1,000 here, that's 25 over 100, and so that is 1/4. Okay, so that's the probability, that's x, but that's not the question we want. Find the probability that Brian does not get an A if he did not study. So we want probability of not A given not study. So we actually want to find this probability, which will be 1 minus x. Okay, so that's going to be 1 minus 1/4, which is going to be 3/4. Okay, and the final part of this video is to talk about independent events. And in doing that, I think it's really important to talk about how independence is different from mutual exclusivity, because it's something that students tend to confuse quite frequently. So we've already talked about mutually exclusive, and that's when two events have no outcomes in common. Okay, so one way we can think about that is if event A happens, then event B cannot happen. So they can't both happen at the same time, okay, because there's nothing in common between them. So for example, the two events rain on Tuesday and no rain on Tuesday are mutually exclusive events. Only one or the other can be happening at a time. We can't have them both happening. And technically speaking, for mutual exclusivity, the probability of A intersection B is 0 because the intersection is empty. Independence is about sort of cause and effect. It's to do with conditional probability. So independence is when the outcome of event A happening has no effect on event B happening, and vice versa. Okay. So for example, you know, two events, rain on Tuesday and my nephew was born on Tuesday, are independent events. The rain is not likely to have caused your nephew to be born, and your nephew's birth was not likely to have caused it to rain. So technically speaking, independence is when the probability of A given B is just equal to the probability of A. So that is the probability of A happening given that B has happened. It doesn't matter that B has happened, that just equals the probability of A. Okay. So since the probability of A given B is the intersection of A and B over B, this means that if we have independent events, A given B is just equal to the probability of A. So that means that the intersection divided by B equals the probability of A. And then if we rearrange this formula, we find that that means that when we have independence, the probability of A intersection B is equal to the probability of A times the probability of B. So in terms of sort of testing for mutual exclusivity or independence, it comes down to essentially working out what's happening with the intersection. And if one of these two things is happening, we might have mutually exclusive events or independent events. Now, let me be clear that you don't have to have one or the other. You know, events can be neither independent nor mutually exclusive. There's no issue with that whatsoever. So independence can clearly be seen in tree diagrams. Okay, so if we have independence, so we know that the probability of, this will be the probability of B, this will be the probability of A, sorry, of not B. This would usually be the probability of A given that B has happened. This would be the probability that A doesn't happen given that B happened. This would be the probability that A happens given that B didn't happen. And this would be the probability that A doesn't happen given that B didn't happen. Now, what we would find if we had independence is the fact that B has happened doesn't matter. So this would just be equal to the probability of A. And this would be the same probability. Okay? Because it doesn't matter whether or not A or B, whether B has happened or whether B hasn't happened, the probability of A happening will still be the same. Okay? So if you're seeing the same probabilities there and there, and similarly there and there, that would mean that you have independence. Okay, so this would just be the probability of not A. And this is also going to be the probability of not A, so they're going to be the same thing. Okay, so that's what you're sort of looking for, that at that second stage in your tree diagram, the probabilities aren't being affected by what happened at the first stage. So that is that the two purple probabilities would be the same and the two orange probabilities would be the same. Okay, so let's consider randomly selecting a card from a standard deck of cards. So just to be clear, standard deck of cards, 52 cards divided into 4 suits, hearts, diamonds, clubs and spades. Hearts and diamonds are red, clubs and spades are black, so half the cards are red, half the cards are black. Each suit divided into 13 cards, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king and ace. So if we consider randomly selecting a card from a standard deck, we're interested in 3 events. A, selecting a red card, B, selecting a spade, and C, selecting an ace. Are A and B mutually exclusive events? So A is a red card and B is a spade. Our spades are all black, so yes, they would be mutually exclusive events. Okay, so yes, mutually exclusive. Oops, exclusive. Since the probability of A intersection B is going to be 0. Are A and C independent events? Sorry, the first question, my apologies, I've read it incorrectly. Are A and B independent and are they mutually exclusive? Okay, so they're definitely mutually exclusive. Let's just be clear about independence. So let's calculate some relevant probabilities. So we know that the probability of A intersection B is definitely 0. In the case of, to check for independence, we want to know whether probability of A times probability of B is also 0. So the probability of A selecting a red card, half the cards are red, and the probability of B selecting a spade, a quarter of the cards are spades. Okay, and so therefore we can say A and B are mutually exclusive. Mutually exclusive. Keep doing that. Since probability of A intersection B is 0, but not independent. Since probability of A intersection B does not equal the probability of A times the probability of B. You'd have to have either probability of either A or B would have to be 0 for them to be both mutually exclusive and independent. Are A and C independent events or mutually exclusive events? Okay, so A is selecting a red card and C is selecting an ace. So we can have a red ace, so they're definitely not mutually exclusive. Okay, so the probability of selecting both a red card that is an ace, there are 2 cards out of the deck of 52 that are red aces, the ace of hearts and the ace of diamonds. Sorry, 2 out of 52. So that's 1 out of 26. So the probability of the intersection is not 0, so therefore they're not mutually exclusive. Let's consider, independence is much harder to determine intuitively sometimes. You actually need to check mathematically whether there's independence. So probability of A, selecting a red card, we know that's a half. And the probability of selecting an ace, so probability of C, there are 4 aces in the deck, so that's 4 out of 52, okay, which is obviously 2 out of 26 or 1 out of 13. Sorry, 1 out of 13. Now, if we were to do probability of A times probability of C, half times 1/13 is 1/26, and so that does equal the intersection. Okay, so we see probability of A times C times the probability of C is half times 1/13, which is also 1/26. Oops. Okay, so therefore A and C are not mutually exclusive. Since the probability of A intersection C does not equal 0, but they are independent. Since the probability of A intersection C is equal to the probability of A times the probability of C. And we've got the numbers there to justify those statements. Okay, so as I said, independence, you need to be a bit careful about trying to intuit whether they're independent. You really do need to mathematically verify whether or not you have independence. Okay, example 4. This time we're told that events A and B are independent. So therefore, the fact that they are independent means that we can assume that the probability of A given B is equal to the probability of A. We can assume that the probability of B given A would be equal to the probability of B. We can assume that the probability of A intersection B is equal to the probability of A times the probability of B. Okay, so we can use all those facts about independence. Okay, so we're told the probability of B is 2/3 and the probability of A given B is 4/5, and we want to find the probability of A. So we know that the probability of A, if the events are independent, is the same as the probability of A given B, and so therefore this is going to be equal to 4/5. We're given that in the question. We want to find the probability of B given A, okay, and the probability of B given A, if they're independent, will just be the probability of B. Doesn't matter that A's happened, and we're given the probability of B in the question. That's 2/3. Okay, and then we want to find the probability of A intersection B. So we know that if they're independent, this will be probability of A times the probability of B. Now, in this case, we're given probability of A, we worked out in part A of the question, so it was 4/5, multiplied by probability of B, we're given in the question, which is 2/3, and so therefore this is 8/15. And then the probability of A union B, so this is where we're going to need to make use of our addition formula, addition rule for probability. So the union is the probability of A plus the probability of B, but then we subtract the intersection because we've counted it twice. And so we've got all those numbers. Probability of A is 4/5, probability of B is 2/3, and we subtract the intersection, which is 8/15. So let's get a common denominator of 15ths. So this is 12/15 plus 10/15 minus 8/15. So that's going to be 14/15. And again, just, simple checks, making sure that your probability is something less than 1. Just in case, you might have made an arithmetic error there and ended up with 16/15, for example. Now that doesn't make any sense, so make sure you sort of take a moment to think about your answers. Okay, two events A and B are such that the probability of A is 0.7, the probability of B is 0.8, and the probability of A union B is 0.94. Determine whether A and B are independent. Okay, so we obviously need to know whether the probability of A intersection B is equal to the probability of A times the probability of B. So we can calculate the intersection because we can use the addition formula. So we know that the probability of A union B is the probability of A plus the probability of B minus the intersection. And we've got 3 of those 4 bits of information. So the union is 0.94, probability of A is 0.7, probability of B is 0.8, and from that we can work out what our intersection is. So we've got 0.94 is 1.5 minus the probability of A intersection B, and so that means that the probability of A intersection B is going to be 1.5 minus 0.94, which is going to be 0.56. Okay, and then we can calculate the probability of A multiplied by the probability of B, which is 0.7 times 0.8, which is also 0.56. So therefore, since the probability of A intersection B is equal to the probability of A times the probability of B, A and B are independent events. Okay, final example. 600 people were surveyed about whether they watched movies on their TV or on their devices. They are classified according to age with the following results. So we've sort of got young and old, for want of a better phrase, although that places myself in the old category, so and TV or device. So based on these findings, is the device used to watch movies independent of a person's age? Okay, so you really just you don't need to use all the different numbers. You really just need to look at whether or not, the probability of whether or not being young in the 15 to 30 age bracket and you watching TV on your TV or on your device is an independent or not event. If one of the combinations, so if you just focus on, for example, these two, if you look at whether they are independent, if they are independent, the other variables, they're all connected, will be independent as well. So you don't need to sort of compare, young people and device, young people and TV, old people and device, old people and TV. You can just pick one grouping, okay? So let's perhaps just go with those first two, so TV and age 15 to 30. Okay, so let's have a think. So the probability that someone is aged 15 to 30 and watches their TV on their TV is going to be 95 people out of 600 people. 95 on 600. 5's a common factor, 19 on 120. Sorry, I could have done that myself, but anyway. Probability that someone's age is 15 to 30. Okay, so that's 290 people out of the 600. So 290 out of the 600. That is 29 on 60. I'm sorry, I'll write it out. 290 on 600 again. Sorry, could have done that. And then probability of someone watching TV is 270 people out of 600. So that's 27 on 60, but 27 is divisible by 3, as is 60, so that's 9 on 20. Okay, and so then we can calculate what the probability of their age being between 15 to 30 multiplied by the probability of TV. That would be 29 on 60 multiplied by 9 on 20. So let's do that multiplied by that, and and we get 29 on 400, which doesn't equal that. Okay, so therefore they're not independent, which means they are dependent. Okay, so therefore a person's age and the device used to watch TV are dependent variables. So there is a sense that, you know, a younger person would be more likely to watch on a device rather than on a TV. Person's age and the device used to watch TV are dependent variables, or dependent events, or whatever you want to call it. Okay, we probably could also have calculated some conditional probabilities there. So again, it would be the sense that, you know, you could have also tested something like, you know, the probability of someone being young, age 15 to 30, given that they watch TV, and testing whether that's the same as the probability of being young. That would also have been a way to test it. So the conditional probability, them being young given that they watch TV, would be 95 on 270, which in its simplest form, 270, would be 19 on 54. And the probability of someone being aged 15 to 30, we already calculated, that was this one at the bottom, 29 on 400. So again, the fact that those are not the same would be another justification for saying that they're not independent, so therefore they are dependent. Or any, as I said, any other combination. So you could have focused on comparing, you know, the young age group with device use rather than with TV use, or the older age group with TV, or the older age group with device. But you don't need to compare all four combinations. If there is dependence between one combination, so in this case we did young people and TV, then there would be dependence between the other variables as well. Because essentially, you know, we have it's all out of 600, so it's all out of, where all of the within this data, the people are either in the young age group or in the old age group, and they either watch TV on their TV on TV, or they use a device. So they have to be one or the other in the data set. So therefore, if one set of variables is connected, the others will also be connected. Okay, so the work today is exercise 13B.